What's up, everyone? How's everyone doing today? Is it as miserable outside for everyone as it is here? Doing pretty good. Doing pretty good. It's just gonna be raining all day today, I think. Okay. So today we're going to be looking at 15.5. So applications of multiple integrals. And really we're just going to be looking at a couple. Honestly, kind of mostly just one. So, oh, so we're going to be looking at, so we're going to be considering finding the mass of, usually the setting is you're finding the mass of what's called a lamina, just like a really thin flat plate in some shape in the plane, if we know its density, its mass density at every point as a function. So usually we're going to denote density as delta of xy. It'll be a function. And so it can be different kinds of density. So usually we'll think of it as mass density. And I'll explain this in a sec. But if you think about distributing charge over a lamina, a thin flat plate, you can talk about the density of charge at a given point. And well, we'll see how you can use that to find the total charge on the plate. And then we can also talk about population density. So basically, the density function works like how you normally think of density, except it's kind of a limit. So so if you think of average density over a region, we'll just make it a square of area delta A. So we have some area delta A. Those for now are point xy is in there. It doesn't really play into it yet, but the average density of over an area is basically depending on what you're talking about. So if it's mass, it's the total mass of the thing, of the region divided by the area. So density is like mass over area, charge over area, population over area, right? Population density is if you have some region, say like 1 square mile, how many people live there? Well, the population density is that many people per square mile. So it's going to be so the mass of region divided by the area of the region, delta A. So if we're talking about mass, that's the average mass density. So basically, if you want to find the limit or the density function at a point, you surround it with some small region, and you look at the average mass, and you basically take that region, you make it smaller and smaller and smaller and smaller and smaller and smaller and smaller, and you take the limit as delta A goes to 0. So it's the mass of a region containing the point xy. Oops. Divided by the area of that region. And you take smaller and smaller areas as it approaches 0. In the limit, we get the density at the point xy. Not super important where that came from, but that is what the density is. So, given the density function, how do we find the total? Right? How do we find the total mass, total charge, total population of some region? So if we have some planar region, some thin flat plate, we'll consider it to be D then we want to find the mass of this plate. So what we're going to do is what we always do. We're going to estimate it, and then we're going to take limits. And in the limit, we're going to get the actual mass. So suppose this is our region D. We know the density function. So what we're going to do is we're going to break it up into pieces, each of which have area delta A, or roughly delta A. The ones on the edge don't, but as it gets smaller and smaller, it doesn't matter. So if we look at in each one of these pieces, we're going to pick one point. Say xij, yij in rectangle ij. So the Rijth rectangle has area delta A. And so if we pick small enough rectangle, if our density function is continuous, which we're going to assume it is, then the density is almost constant on that rectangle. Right? If you have a continuous function and you can only move a very small amount in any direction, the function is not going to change much at all. So the mass of this one rectangle is approximately equal to the density at that point. It's, whoops, sorry. So xij, yij times the area of the rectangle. It's a good approximation because it's a really small rectangle, and the density is almost the same on the whole thing. And so if we want the whole thing, we sum it up. So it's approximately sum up over I and over j. So we do what we always do. We make delta A smaller and smaller and smaller, and as we take it to 0, we get an exact mass. So the limit of that guy is just going to be an integral. So that's the integral over the region D of the density. And that's going to be the total mass of D. So if you want to get the total mass of a region D, you integrate the density over D. If D's mass density, if it's charge density, you integrate, you get total charge, and if it's population density, you get total population. You integrate density to get the total whatever it's a density of. And the same works for functions of 3 variables. So you can talk about the density of a solid region in R3. Then it's a function of 3 variables. And to get that total mass, you integrate the density over the solid region. So for example, let's find the mass. Of the solid region W. Between the plane Z equals H and the paraboloid or elliptic paraboloid Z equals A times x squared plus y squared. And here we're going to assume A and H are both positive. Oh, sorry. We need a density equation to integrate. So given that the density at XYZ is Z. So let's sketch this and then set up our integral. Okay, so we have paraboloid z equals ax squared plus y squared. A is positive, so it's going to be opening upwards, and its z-intercept is 0. And then we also have the plane z equals h, some horizontal plane. So it's going to look like this. So this is our z equals ax squared plus y squared. And it's cut off by the plane z equals h. And everything inside of there is a solid region W. Okay. So we need to do an integral, right? So we want to, we know the mass is just going to be the integral over the region W of the density. So we're doing a triple integral. We need to figure out what coordinate system we want to use, how we want to treat this. Like, do we want to do it in rectangular coordinates and then say z is bounded by functions, etc.? Do we want to use cylindrical coordinates? Do we want to use spherical coordinates? Well, let's see. Okay. So notice, so probably not spherical coordinates. That'd not be my first guess because it's not a region bounded by a cone and or a sphere. But cylindrical coordinates are reasonable because z is bounded above and below by functions. And then when we project this guy down to the xy plane, we get a circle, essentially, right? Or a disk, which is very easy to describe in polar. So let's use cylindrical coordinates here. Okay. So z is bounded below by a times x squared plus y squared. But we're in cylindrical coordinates, so we need to change that to something involving r and theta. What is a times x squared plus y squared in cylindrical? Right, it's a times r squared. And then it's bounded above by z equals h, which when you switch to the cylindrical coordinates, it's still h. Okay, so we have the bounds for z. Now we need to figure out what's going on with x and y, and then use polar coordinates to find the bounds there. So here is maybe the easiest way to do this. So notice the widest part, if we flatten this whole thing down, in the XY plane, the widest part, so it's going to be everything inside this outer curve, the widest part here. And that widest part happens at the intersection of the plane z equals h and the paraboloid z equals ax squared plus y squared. So it's the projection at the intersection of z equals h and z equals a times x squared plus y squared. So the intersection of the two, well, we have z equals something, so we can just set the right-hand sides equal to each other. That's fine. So h equals a times x squared plus y squared. In other words, x squared plus y squared equals h over a. So remember, the projection onto the xy plane is just, you forget about z. So it could happen that z shows up in the intersection, but if you set z equal to 0, so I guess not forget about z, set z equal to 0 and then you're good. But z doesn't even show up, so that's not a problem. Okay, so we have x squared plus y squared equals h over a. In the xy plane, what is that? What curve is that? That's going to be our outer curve. So it's a circle, and what's the radius of the circle? Square root h over a, right? So it's a circle centered at the origin. And the radius is the square root quantity h over a. Okay. Oops. So our region is everything inside of there. So what are our bounds for r and theta? Well, for r, we do what we always do. Take a line, a line starting at the origin through your region. The closest we get to the origin is the origin itself. So r is bounded below by 0. And the furthest away we get is this outer curve, which is, of course, you could just write this circle in polar coordinates, just r equals h square root h over a. Right? If r squared is equal to h over a, so r is equal to square root h over a. So r is bounded between 0 and square root h over a, and then theta goes from what to what? So it's the smallest angle with the positive x-axis. What's the biggest angle? It goes all the way around, so we go from 0 to 2 pi. So setting up our integral. We get, so z goes from ar squared to h. R goes from 0 to square root h over a. Theta goes from 0 to 2 pi. So our density is, we said it was just z. And when we switch that to cylindrical, z is still z. And then dv, remember, is r dz dr d theta. And so let me go through this really quickly. So integrating zr with respect to z, you get 1/2, let me say rz squared, r over 2 z squared, evaluated from z equals ar squared up to h. So we get r over 2 h squared minus a squared r to the 4. So we plug that in to our inner integral. We get integral 0 to 2 pi, integral 0 to square root h over a, r h squared over 2 minus a r to the 5 over 2 right? So looking at this inner guy, integrating with respect to r, so we get r squared h squared over 4 minus ar to the 6 over 12 from r equals 0 to square root h over a.
I think the A is supposed to be squared.
Sorry, what was supposed to be squared?
The A.
You're correct. Yes. Thank you. Yep, you're correct. Thank you. So we get h over 4a times h squared minus a squared h cubed over a cubed, so over a cubed times 12. So we get h in both of these. We get h cubed on top, a on the bottom. So we get h cubed over 4a minus h cubed over 12a. And so we get h cubed over 6a. And then when we integrate that from 0 to 2 pi, we get pi h cubed over 3a, which is correct. Thank goodness. Okay. Any questions about that example? Okay, so to sum it up, total, if you have the density of something, the total of that something over some either lamina, some region in the plane, or some three-dimensional region is just the integral of the density over your region. Okay, so suppose now we wanted to find the center of mass. Suppose we have some region, some thin flat plate D, and we want to know what the center of mass is. In other words, if you sort of think about so if that lies in the XY plane, basically, if this is your center of mass here, it would balance perfectly on a little, spike or whatever. The plate is perfectly balanced if you put it directly on top of something directly above the center of mass here. So our center of mass is going to be, we'll call it X sub CM, Y sub CM. So we're going to basically, so in physics, a lot of properties of a region work if you basically take all of the mass and collapse it to a single point at the center of mass. So that like simplifies a lot of physical problems by just pretending all of the mass is at a single point at the center of mass. There are certain things you can do with that. So in particular, suppose suppose this is our center of mass here. So suppose it's just a single point and all the mass of our plate is concentrated at this one point. So it's just a single point mass. So given a point of mass so our point is at XY and it has mass M. We can look at the moment about the y-axis and the moment about the x-axis. So if you think of attaching this point with the thin massless rod to the y-axis, you can sort of look at the torque about the y-axis that this exerts if you just let it free fall there. So suppose it's sitting in the plane and you let it go and it swings like this. If you're looking at the torque it exerts, the moment it exerts about the y-axis, we can measure that. So the moment of our point about the y-axis. We'll call it capital M sub y. It's basically just going to be the distance of your point from the y-axis times the mass. Sorry, this is maybe unfortunate notation here. So let me say the mass is little m, just so we don't mix this up. So the moment capital M about the y-axis is just the distance of our point from the y-axis. Well, what is the distance of the point xy from the y-axis? So, okay, not just the distance, but the directed distance. So if you're on the other side, it would exert a moment of the opposite sign. So it's basically going to be x, right? So it's going to be the mass times the directed distance from the y-axis. So little m times the x coordinate of your point. And similarly, the moment about the x-axis is going to be the mass times the y coordinate. Okay, so basically, the idea of the center of mass is that so if this is here we go. Okay. So if this is our center of mass, if you collapse all of the mass of this plate down to that center of mass, the moment of the plate about the x and y axes is going to be the same as the moment of the point about the x and y axes, if the point has the same mass as the plate. So in the interest of time, so if you want to see the derivation of this, I guess, go to the book. But basically, so the formula for the x coordinate of the center of mass is just going to be basically, so you integrate y to x times the density over your region D. And you divide by the mass of D. So the x coordinate is you multiply x by the density, you integrate over D, and then you divide by the mass of D. And then the y coordinate of the center of mass is you integrate y times the density over D, and you divide by the mass of D. So I usually try to go through those derivations, but don't have enough time here. And so remember that mass of d in the denominator is another integral that you need to calculate. That's the integral of the density over d. So you can calculate each coordinate of the center of mass using these integral formulas. So for example, let's find the center of mass of plate D so bounded by y equals 1 minus x squared and the x-axis given that the density function is y. Okay. So the first thing I would suggest doing for the center of mass problems is finding the mass of the plate to begin with, because that's going to be in both calculations. So let's find the mass first. Well, hang on. Let's draw our region. We're going to use the same bounds every time. So, okay, y equals 1 minus x squared in the x-axis. So that's y equals 1 minus x squared. In the x-axis, so it's going to hit at 1 and negative 1. The x-axis, of course, is y equals 0. And that's our region D. Okay, so we're doing a double integral. So we have sort of three options here. We could do it as a vertically simple region, horizontally simple region, or polar. So the first two are rectangular. The second option is we could use polar coordinates. How would you like to set up the integral over this region? What seems to make the most sense? So we definitely want to use rectangular, right? Because it's not really a region bounded by anything nice in polar. So let's treat it as vertically simple, right? If you do the vertical line test, there's always a top curve and always the same top curve and always the same bottom curve. So the vertical variable y is going to be bounded by functions. And x is going to be bounded by numbers. So y goes from y equals 0 on bottom, so y equals 1 minus x squared on top. And x goes from what to what? From negative 1 to 1. Okay, so those are our bounds. We're going to use those for all of our integrals because we're integrating over the same region every time. So let's first find the mass. So mass is the integral of the density over our region D. So our density is just y. We said this is a vertically simple region, so we're integrating with respect to y first. Y goes from 0 to 1 minus x squared. And x goes from -1 to 1. Oops, sorry, no, not dA. dy dx. So we do our inner integral. So y, integrating with respect to y, we get 1/2 y squared. Evaluated from 0 to 1 minus x squared. So we get 1/2 times 1 minus x squared squared. Which is, give myself room. That's just going to be 1/2 minus x squared plus 1/2 x to the 4. And so then plugging that in to the outer integral, integral x goes from -1 to 1 of 1/2 minus x squared plus 1/2 x to the 4. So we get 1/2 x minus 1/3 x cubed plus 1/10 x to the 5. X goes from -1 to 1. And so we're just basically multiplying by 2 each time. So we get 1/2 minus, let's see, 2 times 1/2 minus 1/3 plus 1/10. So let's just go for 30. So we get 15 minus 10 plus 3 over 30. So we get 8 over 15. So that's going to be our mass. Okay. So center of mass really quickly. So I'll set up the integrals. Our x coordinate for the center of mass, and we'll talk more about this tomorrow, because this will be important later. So our x coordinate for the center of mass is x times the density which is y. And we use the same bounds. Y goes from 0 to 1 minus x squared. X goes from -1 to 1. And for reasons we'll see tomorrow having to do with symmetry in our function and also in our region. So notice this region is symmetrical in the x direction, so symmetrical about the y-axis. And on the left side, if we look at how our function changes in x as we go out in one direction, it is positive, in the other direction it's negative, and it sort of exactly cancels out. We'll talk more about this tomorrow, but basically we get the center of mass, the x coordinate is going to be 0 for reasons of symmetry that we'll talk about tomorrow. And don't forget about this 1 over m part, because that's important. And I will let you guys evaluate this, but the y-coordinate of the center of mass is y times the density integrated over d. So remember, we already calculated our mass as 8 over 15. So it turns out when you evaluate this guy, you get the y-coordinate is 4 over 7. So our center of mass is going to be the point 0, 4 over 7. And both of those are just evaluating integrals. But this one we could do without actually evaluating the integral using a symmetry argument. I would like to talk more about that tomorrow, but that is mass and center of mass. Any questions about any of this stuff today? Okay, well, I'll be moving over to my office hours Zoom. So the easiest way to reach me is Canvas. I have a few emails I need to respond to still, if that's what you're referring to. But I still prefer Canvas. I've just been really busy the past couple days, so my apologies if you've been trying to get a hold of me. So yeah, I'll be moving over to the Zoom office hours, and I will see you guys there or see you guys tomorrow. Have a good one, guys.